Welcome to AP Podcast 16.4 Gibbs Free Energy. This is another thermodynamic property that we can deal with that helps us understand whether or not a reaction is going to be spontaneous or not. We have dealt with entropy and enthalpy, and here's our third one. So look at this equation because this is one we're going to use quite a bit. And delta G stands for the change in free energy equals the change in enthalpy minus the temperature times the change in entropy. A couple things to remember is that S is usually given in joules and H is usually given in kilojoules. So I'll talk about that a little bit more. We got to be aware of that. But what is going on here is if we do a little bit of substitution, let's say we divide both sides by negative T and then substitute the negative H delta H over T, remember our shoot formula? For S, we get this equation right here. All right? And at a constant temperature and pressure, this becomes very important because this tells us that if G is negative, then the S in the universe is positive. And that becomes super important, this thing right here. Because it's a little more challenging for us to think about the change or the entropy in the universe, because it's kind of tough because we got to consider the beaker, the surroundings, that kind of stuff. But if we get a negative G in our system, that means that we've got a spontaneous reaction. And so this is going to be something we're going to use a little bit more than this right here. And so we've got two values to figure out if it's spontaneous. But in our AP class, we're really going to focus on the delta G, because this universe stuff really plays too many roles. I mean, there's just too many factors involved. But delta G, we can look at our system, our beaker, our flask, whatever we happen to be looking at, and if we get a negative value for G, then we know that reaction is spontaneous. Now, another thing about this formula up here, because I've got a couple mnemonics that'll help you out. A number of years ago, my APers called this the ghost formula. So if it helps you remember it, that's fine. Of course, you guys have a lab, an equation sheet, so it's not a problem. And then a formula, a thing I heard from a teacher that I really, really like is God, I hate this stuff, or gosh, I hate this stuff. So you'll hear me refer to it both ways, probably ghost for the most part, because I really like that, and that's something that my students came up with. So let's look at this ghost formula and see how it applies to a situation. All right, so imagine this scenario where we have solid water going to liquid water. Now, that's better known as what? Of course, you're saying melting, right? So that's melting. And so what we're going to do is we're going to use this ghost formula right here, and the numbers they give us from the entropy and the enthalpy, and figure out if this thing is spontaneous or not, and does it make sense from what we know in real life. So they give us some numbers, so I'm just going to plug it in real quick here. And I've got 6,030 joules per mole, so 6,030 joules per mole, right? And I'm going to subtract that from a temperature of, we're going to do 10 degrees Celsius first. Now remember, look up here. Notice our unit, it's in Kelvin, right? So we can't use Celsius. So let's go ahead and add 10 to 273. So I get 283 K, oops, and I multiply that by this 22.1 joules per Kelvin mole. And when I work that out, I go ahead and multiply those, subtract that from 6,030. The number I get is a negative 220 joules per mole. Now, what do we know about G? Well, we know that if G is negative, like it is right here, it's spontaneous. So let's ask ourselves, will water go from a solid to a liquid at 10 degrees Celsius? And it, in 10 degrees Celsius, I don't know, somewhere around 50 degrees Fahrenheit. Does that happen? Absolutely, it does happen. So that makes sense. Now let's go ahead and do the other one. And I'm just going to erase a number here to kind of make it easier for myself, because the only thing that has to change is this number right here, because a negative 10 degrees Celsius is, of course, 263 Kelvin. And so when I multiply the number out right there, I get, interestingly enough, a positive 220 joules per mole. And so since G is positive, delta G is positive, it's not spontaneous. Now, does that make sense? Is ice going to melt at a negative 10 degrees Celsius? Now, remember, the freezing point of water is 0 degrees Celsius. Well, if your answer is no, it won't melt at that temperature, then all this stuff does make sense. So hopefully I've cleared that up. Now, I do want to give a little shout out to my 2013-14 AP class because I had this all messed up and they helped me fix this. So thanks, guys. Okay, now let's look at this equation because I want you to think about a couple things because oftentimes you're going to be asked to predict whether or not a reaction is spontaneous. And we can do that if we know a couple things. One, we know that G has to become a negative number, right? Well, what can happen for that being a negative number? If H is negative, right, and I subtract a number that, let's say, S is going to be positive, all right, you can see that it is likely, now it's going to kind of depend upon a few things. It's going to depend upon the temperature, but you can see right here that this value, one second, that this value is always going to give us a negative number, right? Because I'm going to take a negative number minus a number, that's going to be negative. So that's going to always work. What would happen if, let's say, for example, the H was positive? Okay. Well, if the H is positive and S was positive, the only way that could really work is if this value right here for T was really big, right? Because it'd be, let's say I've got 100 minus something. This quantity right here has to be pretty big. What about if we had a situation where H was positive and S was negative? Okay. When could that happen? Well, it really couldn't happen, right? Because H is positive minus a minus number, you would never get a value for G that would be negative. So that's never going to happen. And then what if both of them were negative? Okay. Well, the only way that would work is, now if H is negative, that's good, right? If this value right here for T was low, because this negative times a negative number is going to give us a positive number. So we would want T to be very low. So we could predict with that, and you're going to get asked that quite a bit in AP. So let's look at the table. This is kind of what I've just gone over. Definitely want to pause the video here and jot this down because this is a really good table to help you with these predictions. And this is kind of what I just went over. We know S is favorable. That's you know, if a reaction is getting more disordered, that's a spontaneous thing. And exothermic reactions are tend to be favored, right? When they're both positive, okay, the only time that works is at high temperatures. And when they're both negative, that only works at low temperatures. Now, you guys know how I like to associate things. For me, low seems negative and high seems positive. So I don't have a problem remembering this. High temperatures when both are positive, low temperatures when both are negative. And if you can associate that, you'll be okay. And then the opposite, S being negative, which means more ordered, and H being positive, which means endothermic, that's typically not a favorable thing, and you won't get a spontaneous reaction there. So with that, let's try a problem and see what kind of problem we're going to see in one of these examples. What temperature is the following process spontaneous? All right, so you got to ask yourself, at what temperature will it be spontaneous? Okay, so now you can see the temperature that we've come up with. Notice when you set G to 0, you basically get our shoot formula, right? So 333 degrees Kelvin. Now, what does that mean? Well, if we look at this equation right here, that means if this is 333, right, this equals 0. So at what point will this be negative? All you got to do is go a hair above that, and this whole area right here is a negative number, and that makes G negative, right? So in other words, above 333 degrees Kelvin, the entropy value is more important. Now, if we go below 333, think about that. Since H is positive right here, right? Notice it's not a negative number. It's this is an endothermic reaction. Then Below that, it won't happen spontaneously. G will be positive, and the enthalpy value has a greater weight. All right. So we'll practice a number of these problems, and again, like always, if we have questions, we'll start the day with that, and see you next time.